So, how's it coming? So the first step of this should be getting to this, right? We rearrange, we're going to try to solve for x. And now this becomes, you know, kind of like this kind of question, right? Which we haven't quite done yet. And I want to see what have you done to solve this question? We've done a variation, but we haven't quite done this exact one. Can you tell me in language what this says about x? Like, you know, this says that, you know, a number squared is equal to 4, right? This says the sine of an angle is -1/2. Could you tell me what quadrant we're in? Tell me what quadrant we're in. How would you know what quadrant we're in? Well, sine is positive or negative. It's negative. We know where sine is positive or negative. Yes. So we are both in quadrants 3 and 4. So this is the hard part of all of trig, okay? Is that when you are asking for the sine inverse, like, I don't know if you did this, but you could solve this by doing this. Did you do this in your calculator? Okay, and what did you get? -π/6? Ah, okay. So, did your calculator, did you put it in radians and ask for it in radians? Okay, awesome. I love it. That's smart. Okay, so can you tell me what this is in degrees, right? Like for now, what we're going to do is use the unit that you're comfortable in, right? Like, do you know both the Celsius and the Fahrenheit system? Okay, so that's like a tough one, right? What about like kilometers and miles? If somebody tells you like it's 4 miles away, do you have a sense of how far that is? Kinda, right? Okay, so what we're sort of doing is we're building your comfort with miles, right? But every single time we're going to convert it to kilometers so that you can transfer that feel of what that number is, okay? So we're going to talk in radians, but I want to sort of like reference back to like, who is this? What is this? pi/6. What is it in degrees? Okay, so weird. Okay, watch. The number that this is -0.5, and the unit is radians, which we symbolize with a rad, okay? 2 pi is actually what number? It's close to what number? It's like, yeah, it's like 6.5-ish, right? Right? Or not even, sorry, 6 point whatever, right? I think it's like 6.28, right? Okay, so what this says is that there are 360 degrees in a circle, and that is the same as 6.28 radians, okay? Using the actual number of radians is almost never going to be what you see. You're almost always going to see it as a representation of pi over something, okay? in general, you should see this pretty much, like you should start to ignore the pi, and you should kind of just see it as like a 1 over. Okay? Like, of course, it's not the same as 1 over 6. But almost always when you see radians, you're going to see pi on the top. And, like, you'll kind of know. Your brain will, like, there will be alarms that it's not, there's no pi there. Okay? But, like, 11 pi over 6, I see this just as, like, 11 over 6, and that's my old friend radians. I almost see this as, like, the centimeters, right? Like, as the unit symbol that means radians. Okay? Okay. All of that is to say, what I mean by this is, what is this in degrees? So this is negative pi over 6, so I will almost never refer to this as like negative a half, but it's about negative a half in terms of a number that you plug into your calculator. But because we need pi, that means when we turn it into a decimal, we make it imprecise. Pi is very, very precise with its infinite decimals, so we're going to keep pi in there, okay? So negative pi over 6, what is that in degrees? Just remember what it is in degrees, because you have your feel in degrees. What is this in degrees? Negative 30. Beautiful. Okay, so then what is the related acute angle? Yeah. What is the principal angle? It's not. It's not. The principal angle has to go to the same spot. What quadrant are we in? No, negative 30 is start at this spot and go negative 30 degrees, right? So what quadrant is this? Yeah, and is that right? Should we be in the fourth quadrant? Why is it right? Who did we point to say, yeah, we're right here? Good, because sine is negative. Okay, so then where's the other spot where sine is negative? Yes. Okay, and so it should have the same related acute angle, right? So it should have the same related acute angle. And so what has a related acute angle of pi over 6 and is in, like, this is all you're going to have for bits of information to go on. Your calculator will not give you this number here like it gave you this number here, okay? So it's your job to do this step. And this is where, like, you can lose a lot of marks sometimes, is where you just say there's one solution. There's actually two, okay? So there's two that have the same related acute angle. What is the angle that has the related acute angle, or the same related acute angle, as negative 30 degrees? That is in the third quadrant. Good. Yes, 210. Right? Awesome. So how did you get there? Beautiful. Good. Okay. So, okay. Can I ask you, what is, like, because this is not really allowed, right? We need angles that are positive. So what is that angle really? Remember the trick. If it's negative, just add one revolution until it's positive. Right? So what's one revolution of on top of 30? Oh, sorry, negative 30, right? Yeah, good. Okay, now the challenge is in radians, right? So this needs to be 330. How do we do that in radians? There's going to be a pi in there. Right? What is it going to be? Yeah, that's totally a valid way to do it. Right? That's a valid way to do it. Another way to do this is that what you did was 360 minus 30, right? 360 is 2 pi. Minus 30 is pi over 6. Well, 2 pi, let's just make that a multiple of 6. So that's actually 12 pi over 6 minus a pi over 6. Okay? So what is that? What is it? No, not a single pi over 6. 12 pi over 6 minus pi over 6? Yeah, good. Right? So see how you can kind of like, do you see that? Can you see that looking at that? How that's one away from a perfect pi over 6 rotation of 12 pi over 6? Like, that's, like, do you agree that it's easier to see the related acute angle looking at that angle there? Even though it's uglier to like think of, and it's not like, it's a little foreign, right? The feeling of kind of like translating that and doing all that. Seeing the related acute angle there is like so much better, so much easier. Okay. Okay, so what is 210 then? Let's try to think of it the same way. What's this? $210 is what? So 210 is how many pi over what? How many pi over what? So we need it to go to this quadrant, right? Which is a pi plus the related acute angle. Right? That's our 210. Which is pi, a whole pi, so not 2 pi's, minus, right? The question is pi plus the related acute angle. What is the related acute angle? The related acute angle is pi over 6. Okay. So you're always going to do one of these operations. And so once you nail down your related acute angle, it's just about kind of plugging it into, you know, this is just the related acute angle. Right? And this is quadrant 1. Quadrant 2, quadrant 3. So if I ever have to get places, this is how we get there. Okay. So we needed to get to quadrant 3. So we did pi plus our related acute angle. Right? And we got, well, this is really 6 over 6, so you just use this denominator to put that sort of imaginary 6 over 6 there, and you end up with 7 pi over 6. So that would be, those would be our two answers to this question here. Okay? That would be the two solutions to this equation. So there's two solutions. A lot like, you know, when you've done quadratics, there's two solutions to the answer. Or two solutions to the problem, right? Okay, so this strategy here is going to be sort of like, you know, what's so comfortable, what's so nice about radians, and you'll forget about degrees in this world, okay? Okay, do you want to try to solve this one? We're going to use the same method. We're going to rearrange to the point where we get a sine inverse or a cos inverse. We're going to, from that value that our calculator gives us, we're going to get a related acute angle, and then we're going to have to think of everything that works with that same related acute angle. Okay? feel comfortable trying that? Okay. Let's do it. Okay, so did you get to this stage here? Okay. Can I ask whether you did both the positive and the negative square root? Okay, you did do it. Awesome. That's great. So that's important, right? Because whenever we do the square root, we have to be ready for both the positive and the negative. Okay, so that means that we're going to have actually two different sort of like routes to go here. So we're going to do both the positive and the negative. And so let's kind of tackle that. And each of those are going to give us 2 like this one did, right? Because that one gave us 2, and that looks a lot like one of these ones, right? Okay, so we're actually going to get 4 answers here. Okay. So, what did your calculator tell you with the cos inverse of that? What do we get? What is our cos inverse? $30. Okay, is that a related acute angle? Yeah. It's our related acute angle too. Okay. So anything that's between 0 and 90 is our related acute angle. Okay, so what's the other? You know, there's another arrow here. What's the other cos inverse? The hidden cos inverse. Why? Is that where cos is also positive? Okay, what quadrant is that? Yeah, so quadrant 1 and quadrant 4. Okay, what quadrants are these going to be in? Okay, so we have all 4 quadrants. And what are the related acute angles of these ones? Yes, but the related acute angles? Yes. Um, 120 and 210. Okay. Okay, can I ask what the related acute angle of these are? Of this? Sorry, this was a copy paste, sorry. What is the related acute angle of 120? It's 30 away from 180? Yeah. Okay, but then what was the related acute angle of this one? Something's up here. Should it be 60 or 30? Yeah. Alright. So who's wrong? 210 or 120? What should it be? 150. Yeah. Good. So they're going to have the same related acute angle, but they're all just the, you know, all 4 different quadrants because it's both the positive and the negative. Right? Okay. So now it's our job to convert these actually to... sorry, who was this one? What was this one? Yeah, good. So now it's our job to convert these to radians. Right? What is this in radians? Sorry, I have to close this program every so often. Okay, can you see that okay? Okay. Five or 6. Good. Nice. 1 pi over 6 away from 12, which is 2 perfect ones. Right? Okay, what about 150? We're a little bit less than a whole perfect pi. Nice. It sounded like that one was a conversion where you started with 6 pi over 6 and you went to 5. Is that right? Okay, cool. That's how I want you to sort of... That's an easy way to think of it, okay? Because you're going to see related acute angles a lot easier once you just see angles, okay? Okay, so what about this one? This one is a little bit past the full pi, right? 210. So what is this one? Yeah, good, right? Because remember, a whole pi is 6 of them. And so it's a little bit past it. A pi over 6 past it. Yeah, good. Okay. Yep, so that is our solution for that one there. Okay? So this is kind of like, it seems pretty harmless. Like, oh, okay, there's going to be 2 answers, but there's actually 4, right? And I could play with this even more by adding a little 2 in there, right? Because then if I had made this 2, then this actually is, you know, this is actually 2 times the value that I'm looking at, right? Or 2, you know, it's a 2x, right? Well, what that means is like, you know, what would have been too far, right? Because this is the 2 pi line, and that's where I told you to stop, right? Because there's another one here that's like 13 pi over 6 that's just past 2 pi. That is 2 pi, you know, a pi over 6 past 2 pi. That is the sort of, you know, that's the continuation of this pattern, right? Well, if this is twice, if I put a 2 in here, well then I'm going to sort of like fit 2 of these cycles. It's like I'd sort of take all of them and I squish it and I do this. So now there's going to be twice as many. So you're responsible for twice as many. Okay. So you'll see that, you know, that's a sort of metaphorical version of what what you might see, but I'm trying to just sort of like, you know, shed light on how this might vary. Okay. Okay. Let's take a look at some trig identities. I mean, you're pretty good in this world. Like, we're ready for pretty much any question now. But I think something else that might be worth doing is also looking at application. Like, you know, Billy drops a ladder and it falls across the whatever, right? Like, those types of problems. Okay? The only other thing is a trig identity. Okay? So for trig identities... you're pretty much only going to need to remember the Pythagorean identity, which is, what is this equal to? 1. Yeah. And then really, like, this becomes a way to rewrite sines in terms of coses. Okay? So if you need things to be in coses, then you can do it this way. If you need it to be in sines, then you can do it that way. Okay? So this is the 3 variations of the trig identity that you really, really just like need to know and memorize and be comfortable with and see easily, okay? In general, like, it seems reasonable sometimes that you're like, oh, 1, that could be rewritten as this. In general, you're not doing that. You're making things easier. So don't look to make things more complex in general. But this, you know, is somewhat making it more complex, but it's a useful one, okay? In general, if you see a 1, don't ever convert it to this, okay? But, you know, of course, we can play with that rule. Yeah, but it's very rare. Okay, for the most part, you'll see it if it happens. Okay, so that's important to use. The other thing is it's just about spotting, you know, normal math patterns. Okay, so normal math patterns that have nothing to do with the trig. So normal math patterns like this. What is the thing that you should do to prove this statement? These are fractions. So what should you do with the left side to prove that it's equal to the right side? Well, what do you mean by solve it? Yeah, how do you add it? Yes, common denominator, right? So when this looks like sine of theta and this looks like cos of theta, then your common denominator should look like that, right? But the operation has nothing to do with the trig there, right? It's just about the fractions themselves doing the common denominator, okay? This is the stuff that has actually has to do with the trig. Oh, don't delete that. Okay. So for the most part, we're just going to be doing this type of stuff, okay? Common denominator. Another type thing that we might see is something like this, right? Like you can have this plus that times the green thing, right? Well, this is an opportunity for common factoring. What's common factoring? What do I mean? Yeah, right? Like I can write this as this, right? Okay. And the last one that you need to spot is this one. What is this? Yeah. This is like, we love to do this. And this is like, especially if you want to turn things into squareds, you can do that using the not squareds, right? Pretty easily. And then look, this is a difference of squares. This is a difference of squares, right? So we end up seeing this a lot, okay? Difference of squares. Okay. If you can sort of hang on to these three patterns and you know this trig identity, then you're in good shape to tackle anything, okay? And your job is to sort of like simplify the complex side. You know, this is your job. Simplify the complex side into the simple side. But don't be afraid to play with the simple side. Like what you're trying to do is metaphorically kind of like build a bridge from here to here. And sometimes it's unreasonable to sort of like, once you get to this point, to try to build the last little section to here. You can sort of like go backwards, and then you can just pretend like you didn't go backwards and just go back to this. Okay? So metaphorically, I hope you know what I mean. Kind of like just play with the right side just a little bit to get it to look like the left side, and then go back and make it look like you never did it. Okay? Okay, so let's try a question here. Let's try a trig identity. Let's see here. I do have to get running at 5 here, but I think we can tackle these pretty easily now. Okay. So let's try. Oh, sorry. We also forgot about our old friends, secant of theta and cosecant of theta and cotan of theta. What do these mean? Yeah. Who's who? Cotan, I'll give you, is tan of theta. Give you the easy one. Yes, good. The way that I remember it is like the co part, right? It's like sine and cosine. It's secant and cosecant. So you're never going to get the two co's together. So it's always like a co with a non-co. So it's cosecant and sine, right? And then cosine and secant, right? Okay, cool. So that's something you're going to need to. Okay, so let's try this. Let's try secant of x minus oh, wait a second here, actually. That is something that I want to test. Why is this looking so crazy? Okay. Wait a second. Okay, let's try this. Cotan squared of theta plus 1 times sine squared theta minus 1 is equal to negative cotan squared. So what do we do? Oh, and tan of theta, this is something we've already said. Tan of theta is sine over cos. So the procedure is generally going to be turn everything into all into cos and sine. So just turn everything into sine and cos. Unless it's like everything is in tan or everything is in, you know, cotan or something. But if you have like mixes, just put them all into sine and cos. Okay? So cotan is what? Good. And what does it mean that when I put that little 2 there? Yeah, the whole thing, right? So this is cos squared theta over sine squared theta. You with me? Plus 1. Okay. And then sine squared theta minus 1. And negative, this is the same thing. Yeah, good. Cos squared theta. Beautiful. Okay. Now what? Ooh, I wouldn't go there yet. I wouldn't go there yet. Not yet. You can make your life easier. You could, but remember, the goal or the trick or the benefit of difference of squares is that you can turn not squared things into squared things or squared things into not squared things. Do you need to get rid of the squared things? Not really. We have squares on the left and squares on the right, right? Okay, so the only one that's left then, we have a common denominator opportunity here. Right? That somehow has to become one big fraction. In fact, there's two common denominator opportunities. Right? Oh, no, sorry. This one isn't a fraction. Right? So that is a common denominator opportunity. But what does that look like? What's the denominator? Yeah. And I have the fraction 1. Or really 1 over 1. Right? Beautiful. Good. Now, there should be some alarms going off here. Yes. Now your life is so much easier, right? And look. That is the denominator that you've been looking for over here. Now it's the only denominator that you have. So that's a good thing, right? So, okay. There is an opportunity to expand. In general, you don't expand. Okay? In general, you're not going to expand. So, like, that's a last-ditch effort. Okay? On the scale of doing things, look for common denominator opportunities. Look for common factoring. No, actually, I would probably put difference of squares above common factoring. But, you know, those three. And then maybe there's like... okay, well, I'm comfortable putting kind of expanding number 4. Okay? So look for it last, okay? Because we just don't see it all that often in these questions. Okay, so then that can become 1. Awesome. So I'm just going to kind of... There's a luxury here. Copy, paste. Okay, now what? Oh. Oh god, what's going on here? My hand is touching the pad, I think. There we go. Okay. 1. Okay. Now what? I mean, is it okay if I write this as this? Okay. So now so in general we don't want to mix both sides, okay? Because watch how you could cheat. Okay? Watch. Multiply both sides by 0 and I can make this statement true. Right? So that's the only problem, okay? In general, I can manipulate 3 and 4 on their own, but as soon as I start to combine them, I can accidentally make that mistake. Okay? So let's try to do it without. Let me ask you this. Like on the left side, you have a fraction. On the right side, you have a fraction. Are the denominators equal is the most important question when you have two fractions equal to each other. The denominators aren't equal to each other right now? They are. which means the numerators must be equal. Okay, so look, you use this twice in this question, and it's both times the kind of critical point of the question. The only other thing was to get the ball rolling, a common denominator. Okay? So that's like pretty much how these questions go. And like, are you comfortable with the fact that it's not 1 minus sine squared theta, right? That is equal to cos. So what does negative cos have to do with this? Yeah, so we can rewrite that as this, right? We can flip the order and still do a subtraction, and it's equal to the negative of it. Okay, cool. So then, okay, yeah, we've proved it, right? Okay, in general, like those are trig identities. Like you just convert things into sine and cos. You probably have 1 or 2 math things to do first before you dive into any of the trig. Then you'll probably have to spot the Pythagorean identity in maybe 1 or 2 forms, right? And always keep in mind your target, right? Like we used this as a target as to why it wasn't necessarily a good idea to expand, because what's the likelihood that it kind of simplifies to this, right? We're going to get something crazy. If we can do something another way, let's do that as a last-ditch effort because it's probably going to take the most work, right? And yeah, in general, expanding is a form of like making more complex, and our job is to simplify, right? Okay, cool. So I have to get running, but I will send you this note. You're pretty much ready for all of trig now, okay? So I know we kind of jumped around a lot, but like, you know, a lot of this you'll find is pretty much what you're going to be tackling throughout the unit. Where are you right now? You're sort of just doing... Oh, we haven't really talked about the graph of things, so that's kind of the second half. Okay, cool. Yeah, that's kind of just the second half of this, is like turning this all now into like X and Y graphing, like doing transformations of graphs and all that. Okay? Okay. Cool. Awesome. All right, no problem. Good work today. We'll see you soon. Okay, bye. Have a good night.